This is the introductory lesson to the AQA A-level chemistry topic, Group 7, the halogens. As always, I'm going to ask you to work with the booklet and try the tasks as you're going through, pause on the tasks, and then review the answers. Double check on Teams if you have any questions during the lesson, or email outside of the lessons. But I do want you to be really working hard to deepen and embed the learning. So we're going to get straight on and we'll take a look at the initial objectives. And you can see, just like we saw with Group 2, we're going to look at some of the periodic trends, so atomic radius and electronegativity. So there's a huge amount of what we're about to do that will be, once again, familiar to you. Let's get on to the first task. And we have here a prior knowledge check. If you can have a go at answering these questions relating to electronegativity, pause and then review. Okay, so let's take a look at the answers. We have got, for electronegativity, the power of an atom to withdraw electron density towards itself. Now, that can be worded in different ways. It can be the ability of an atom to attract electrons towards itself, would also be fine. However, at the moment, this definition is incorrect. If this is all you've written down, when you add the correct answer and the extra bit, please highlight it, please annotate it so that you know it's something that you'd forgotten. Because if you're going to get credit for the mark, you have to say it's from a covalent bond. So then we start to look at the trends. What is the trend in electronegativity across a period? Now, we've already done this with period 3 in the periodicity topic. Hopefully, you've remembered that it increased. And then when we start to look at the reasons why, in the first instance, there's an increased nuclear charge. Each subsequent atom has an extra proton, and that's pulling on the electrons on the outside and therefore within the covalent bond. But it's not the only reason. It's also the fact that there is no increase in shielding. So you've got a nice little two-marker explanation there for why electronegativity increases across a period. If we then look at what happens down a group, it decreases. And again, if we try to think about why, as you go down the group, you're getting a larger atomic radius. The electrons are further from the nucleus. And if they're further from the nucleus, they are less attracted to it. So the nucleus has a lesser pull. But there's also an increase in shielding, that repulsion by inner electrons pushing out against those electrons in the covalent bond. So again, 2 marks there to explain the trend down a group for electronegativity. Just taking a look, we know that electronegativity tends towards fluorine. That's the highest electronegativity. And that also helps you to remember trends within periods and groups. But it's also a good point to discuss the fact that it isn't the case for group 0. Because based on what we've said so far, you might think that neon has the highest electronegativity. Or helium, indeed. But they don't form covalent bonds. And so that's again where that definition becomes really, really important in terms of understanding what we're looking at. Okay, next task, we're looking at atomic radius. See what you can do, pause. And now let's take a look. So the trend in atomic radius across a period sometimes comes as a little bit of a surprise to people, but it is a decrease, it gets smaller. The reason for that is because there's an increased nuclear charge. We've got an extra proton, sounding familiar here, got an extra proton, which is pulling on those outer electrons more, pulling them in closer. And there's also no increase in shielding. You've still got the same number of inner electrons pushing out, repelling those outer electrons. Now, that is quite important because that's identical to the reason that we spoke about in terms of electronegativity. And it actually also helps to explain the general trend in first ionization enthalpy. So finding those links and finding those groups can be of huge, huge importance to you. Okay, let's take a look at down a group. Normally a more straightforward one, hopefully quite straightforward. It increases. And the reason why is that you've got an extra principal energy level every single time as you go down the group. So that means that the outer electron is further away from the nucleus, and that's really what atomic radius is. But there's also an increase in shielding. Each subsequent element has got more inner electrons repelling the outer electron. So the outer electron's further from the nucleus, and the atomic radius gets bigger. And this might seem a little bit repetitive, but we've spoken in general terms across a period and down a group. So what could we say about electronegativity and atomic radius down group 7? And there's also an opportunity here to think back to the bonding topic, where we can think about the trend in melting points. Do your best to have a go at each of these three and then review your answers. So pause. Okay, and let's move on. So the electronegativity, we've just said, decreases down a group because there's an increased atomic radius and there is greater shielding. So we're just applying what we've spoken about to the specifics of group 7. And we have already said that down a group, atomic radius increases. So that's true for group 7 because there's an extra principal energy level, outer electrons are further from the nucleus, and there is an increase in shielding. In terms of the melting points, this is a really important one. And as I say, it goes back to work that you've done in bonding and specifically intermolecular forces. The trend is that it increases. Now, there might be other ways that you can remember this. If you can remember that fluorine is a gas, chlorine is a gas, bromine is a liquid at room temperature, iodine can be a solid at room temperature, a blue-black solid. So we can see there that there's an increase. But in terms of the explanation why, the molecules are getting larger. They have a greater surface area. You can also link this to your knowledge of hydrocarbons and increasing chain length, the impact that that has on boiling points. So lots of cross links here. There are stronger van der Waals forces because they are larger molecules, because they have a greater surface area. And therefore, they require more energy to overcome. So the melting point is higher. Okay, we're going to move on to look at some of the chemical reactions of halogens now. We're going to look at one specifically in this lesson. And this is the displacement reaction that you will hopefully be relatively familiar with from GCSE as well. So we need to be able to talk about the trend in oxidizing ability of the halogens and provide experimental evidence to confirm this trend. So at GCSE, we spoke about this as an order of reactivity, which is the most reactive halogen, which is the least reactive halogen. And there will be a method that you will have carried out where you react chlorine, bromine, and iodine with salts of chlorine, bromine, and iodine. And if it's still sounding familiar but a bit vague, I'm going to move to the results table now that might help you to remember it. And this is what you would probably have drawn out or filled in. And we can see that when I add F2 to KCl, my colourless solution goes green. When I add bromine to potassium iodide, my red-brown solution goes to a dark brown solution. And so we're starting with the colour of the halogen. Chlorine, for example, with KBr, starts pale green, the colour of chlorine. It ends up red-brown, the colour of bromine. And that's going to be important when we start to consider the chemical reactions. So, I'm still going to keep this table visible for you. We're going to move on, and I would like you to have a go at these two questions. So, pause. And now let's take a look. So, we have got The 4 reactions that were not carried out, we've shaded them. Well, is there any point doing F2 with KF? If the halogen is merely displacing itself, you're not going to get a visible change. It's pointless doing it. In terms of the reactivity, well, what we're seeing is that fluorine is the most reactive. Fluorine can kick out chloride, bromide, and iodide ions from their salts. Iodine can't kick any of them out. So that's our start point, but we're going to build on that a little bit more. I'd now like you to consider this question and try to write out the 6 equations that where the reaction has taken place. So they're the 6 on the right hand side that are not no visible change. Have a go at them, and when you're ready, move on and we'll review. So let's take a look at the first one. I'm going to go through sequentially, F2 with KCl. Well, if we're talking about the halogen kicking out another halogen, we get this straightforward displacement reaction that was discussed at GCSE. F2 and 2KCl go to 2KF and Cl2. And I'm going to go through the remainder of these a little bit more quickly. The colour coding will continue so you can see which box they relate to, but you might want to pause so that you can check once all 6 of them are up. So here's the next one. Equation number 3. Equation number 4. Equation number 5. And equation number 6. And obviously for all of the ones that are no visible change, there is no chemical reaction, no equation to write. But we're going to move on and start thinking about ionic equations now. I want you to take the example of chlorine water and potassium iodide. Use all of the knowledge that you have, everything that you can recall, to try to write out the ionic equation and then break it down into its 2 half equations. We're into the redox topic now as well, actually. And then once you've done it, want to know what's been oxidised, what's been reduced, what's acting as an oxidising agent, and what is acting as a reducing agent. So pause. And let's take a look at the answer. So we'll begin with the full equation. My Cl2 reacting with Ki, making 2KCl and I2. In an ionic equation, we break down anything that's ionic and aqueous. So I can break down my Ki, I can break down my KCl. But Cl2 and I2 are covalent, so they stay as they are. Now, once I've written this out, I can start to determine what's not needed. I look for spectators. And in this particular case, I've got my Cl2 and 2Cl-, they've changed. My 2I- has become I2, that's changed. But my 2K plus has remained as 2K plus. So I can get rid of those as spectators. That then allows me to simplify this ionic equation, and you can see the finished version here. Now, from there, I am going to break it down into the half equations. So that's taking each component part, the Cl2 becoming 2Cl- and the 2I- becoming I2. And now I need to balance them, and we balance these with electrons because we're balancing charge. So in the Cl2 example, I add 2 electrons on the left, and in the I- example, I add 2 electrons on the right. Now there's a couple of ways that we can then look at this. If I go to the top example, this is reduction. And it's reduction because we are gaining electrons. And remember, oil rig, oxidation is loss, reduction is gain of electrons. But there's another way that we can see that this is reduction. The Cl2 has been reduced to Cl-. The oxidation state has gone down from 0 to -1. Another word for go down is decreased. another word for decrease, is reduce. If you reduce the oxidation state, it's reduction. If I take a look at the second example, you can see that it's oxidation because electrons have been lost. They're now separate on the right-hand side. But also, I've increased the oxidation state of iodine from -1 to 0. If you increase the oxidation state, it's oxidation. I'm actually going to talk more next lesson about oxidizing agents and reducing agents, but anything that's reduced acts as an oxidizing agent, so that's Cl2, and anything that's oxidized acts as a reducing agent, so that's I-. So we're going to carry on thinking about this. There's a question that I would like you to consider. What's the best oxidizing agent in group 7, and what's the trend in oxidizing ability as you go down group 7? Try it, pause, and then move on. Let's take a look. The best oxidizing agent is F2 of the 4 examples that we saw, and actually it is the best because it's at the top of the group. We know that because it was able to oxidize every other halide in the chemical reaction. Now, if that's the most or the best oxidizing agent, we can assume that it will decrease down the group, but we have further evidence of that as well. We know that I2 could not oxidize any of the halides above it. And if you actually do a little tally chart of how many bromine can oxidize and how many chlorine can oxidize, you will see there is a very clear pattern. Oxidizing ability of the halogens decreases as you go down the group. Final task for today, and we're going to take a look at this example. It's a practical use of this reaction, and it's about extracting bromine from seawater. It's also another great opportunity to practice doing your ionic and half equations. So let's try it. Let's see what we can do. Pause. And now let's review the answers. So my ionic equation, I've actually left out the K plus or Na plus, whatever it might be, immediately because we were told that the bromide ions are reacting, and this is what we have. It's not finished yet because we need to balance it. Now, once we've balanced it, we can build our half equations. My Cl2 goes to 2Cl minus, my 2Br minus goes to Br2. I add the electrons to balance charge, and we have everything we need. We're then identifying what's being oxidized and what is being reduced. The chlorine is being reduced to chloride. The oxidation state has been reduced, so it's reduction. It's also gaining electrons because the electrons are on the left. Bromide ions are being oxidized to bromine. The oxidation state is going up, and we know it's oxidation because electrons are being lost. We know they're lost because they're added on the right-hand side. And then, finally, as I've already touched on earlier, if something is reduced, it's acting as an oxidizing agent, and if something is oxidized, it's acting as a reducing agent. So that brings us to the end of lesson 1 of group 7. We'll be continuing with this next time, and once we've got through group 7, we'll be doing a lesson or two where you'll be able to do some exam practice and actually put all of this theory into practice, as you might be expected to in the summer. So thank you for listening. Any questions, get in touch, and I will see you again next lesson.